so we're going to go ahead and get started. So today's presentation is going to be on 3D scanning for reverse engineering and inspection. Hopefully this is the class that everybody signed up for. So just a little bit about me and a little bit about NeoMetrix. So my name is Perreault. My company is NeoMetrix. Of course, we do 3D scanning and reverse engineering, the subject that we're talking about this afternoon. We do that both as a service, and then we also sell equipment and software. Additionally, we sell 3D printers and provide 3D printing services. So a little bit about scanners. There are a lot of different types of scanners on the market. And what I like to say is that scanners are like screwdrivers. So why do I say that? Because not one tool is good for every job, right? So there are long-range scanners, there are short-range scanners, there's laser, there's white light, there's handheld, there's tripod mounted. There's a lot of different tools out there. And each is going to be good for certain applications. So the scanners that you see there sort of in the top middle of the screen are two from Perreault, which is the HandyScan Black and then the GoScan Spark. So that's kind of the primary tools that we use in our business and the tools that we sell. We've also got articulating arms like that Romer system, which has a hard probe on there. Those are kind of useful for doing probing measurements like hole locations, things like that, as well as combining it with scanning. You've got the tripod mounted scanners like that EVIC scan there. Those are going to typically be more high resolution for smaller parts with a lot of fine detail, but maybe not going to be quite as easy to use or as portable as some of the handheld systems. So I guess when you're looking at a scanner or looking for a scanning service, you're going to want to identify what is the tool I need for the type of job that I want to accomplish. So as we mentioned kind of on the first slide, there's really two different applications for scanning, or let's say two primary applications. The first one being reverse engineering, where we scan a part and that gives us either a point cloud or an STL file, and then we can convert that to a CAD model for reverse engineering. Or you can take that data and overlay it on an existing CAD model for inspection. So we're going to kind of touch on both of those applications today. So for our purposes, we're talking about reverse engineering is creating 3D CAD files from scans. So before we get too deep in some of the methodologies, I just want to go over some of the terminology that we use in this industry. One of which is digitizing. That's kind of an older term. Back when we had mechanical digitizers and hard probes and CMMs and that kind of thing, where you're taking individual points on a part and creating a digital copy. So that's kind of where that term digitizing comes from. 3D scanning is really digitizing by using an optical device, like a laser scanner or a structured light scanner, where you're getting millions and millions of data points. So it's really like digitizing, but in a faster, more densely populated method. So your scanning and your digitizing will typically produce this cloud of points, or a point cloud. So every data point you capture is going to have an XYZ location in space, and then we get millions and millions of those that define the shape of an object. Now if you connect the dots of those point clouds with little triangles, that gets you to that polygon mesh, which we'll typically save out as an STL file. Once you get that polygon mesh, then you can develop a solid model or a CAD model through reverse engineering techniques. So when we talk about CAD models, in my world, there's really sort of two different types. You've got a surface model, which is really like a skin, or an infinitely thin skin of, let's say, one side of a part. And then you have a solid model, which is basically a volume in space that is fully enclosed by those surfaces. So if you've got a solid and you delete one surface of that solid, then you're going to end up with a surface model. And so we're going to go over in a little bit of detail the different techniques that we use to create those solid models. So for, let's say, mechanical parts, we do more parametric or feature-based models, and or more organic parts, we'll do more of the rapid surfacing or auto-surfacing techniques. So choosing your modeling method. this is what I like to say, it's really about bricks and potatoes. So a brick being a very good example of a feature-based model, right? It's got 6 surfaces that define that shape and that's it. Whereas if you look at something like a potato, if I gave you a potato and said you need to create a solid model of this in SolidWorks, that would give a lot of people quite a bit of heartburn because it's a very free-form organic shape. Okay, so for our potatoes and our organic shapes, we typically use what we'll call either rapid surfacing or auto surfacing. So if we scan a part, typically if we're using like a tripod mounted scanner, we'll do it in 2 different positions. So you can see we've got 2 chunks of data there. We will register or align those together, then merge them into a single polygon mesh. That's kind of our starting point. Then we have defining patches. So we create a network of curves on that mesh that will then define the boundaries of the surface or our surfaces. So it's in the defining of those patches that kind of designates the difference between manual surfacing, auto surfacing, or like rapid surfacing, which is sort of going to be an in-between manual and auto. So auto surfacing is you click the auto surface button, it develops all those curves for you and fits the surfaces, which is great, but sometimes it may run into some issues where you won't necessarily get a solid model when you're done. You may have some twisted up surfaces causing some holes, and then now you get that surface body instead of a solid. Whereas if you use manual surfacing, you can define all your curves and your patches on your own, but that may be very difficult and time consuming on a very complex part. So that's why in between with the rapid surfacing techniques, where you'll start off with an auto surface patch layout, but then manually edit those areas where you'll run into problems, is a nice in-between technique to use. So once you have those patches defined, then within each patch, a surface is fit, and that's what creates that solid model. And then finally, we like to compare back to the scan data we started from to see how accurate our final CAD model is to the scan data that we started with. So rapid surfacing and auto surfacing are very, very accurate, right, because you're directly fitting that network of curves onto your underlying scan data, but you don't end up with a, what looks like an engineered model. It's going to be very organic in nature. So that's kind of why you probably wouldn't want to use that on a mechanical part. So next we have parametric or feature-based modeling. Again, we're going to start with our scan data. Instead of shrink wrapping a network of curves onto that, what we do is we create sections from which we develop sketches and then use those sketches to create our solid bodies through traditional solid modeling techniques like extrude, loft, sweep, revolve, all the stuff that typical CAD users are familiar seeing. Once we have our final CAD model, then we can send that over to our native CAD software either by saving out a step file or other neutral format, or doing what's called a live transfer, depending on the software you're using, where the system will rebuild your parametric model in your native CAD program. Now you may need to employ a technique that I call hybrid modeling, where maybe you've got some mechanical features and you have some organic features, so you can combine both of those to get your final CAD model. So you can see over on the right side we've got a medical device housing. The exterior surfaces were very organic, so those were rapid surfaced. And then all of the ribs and bosses and other mounting features were then feature-based onto that underlying surface model. So to perform all of these tasks, we typically employ Geomagic DesignX as kind of the Cadillac of reverse engineering software. It has all the tools to allow you to edit. Good afternoon. To edit your 3D scan data, take your point cloud, create the STL, and then offers both manual surfacing and rapid surfacing, as well as the parametric and feature-based modeling techniques. Okay, moving on to inspection. So inspection is going to be taking our scan data, and instead of creating a CAD model, we're going to compare it to our existing design. So if we look at traditional measurement and inspection techniques, you've got your hand tools, calipers, height gauges, tape measures, micrometers, stuff like that. Those are really one-dimensional tools, right? I can pick up a length, either up and down, or the length of the part, that kind of thing. Useful for very simple parts, not so much for really complex geometries. Then you have CMMs, or coordinate measuring machines. Those are great for free-form organic shapes. They're very, very accurate, but they require very specialized, complex software, and they can be very complex to program. So if we compare that with scanning for inspection, so of course when we use a scanner, we're going to capture a lot of parts to define the whole object that we're working on, overlay that scan data onto our CAD file, and align that, depending on what type of methods you need to use there. And then you can either do a 3D color map to show deviations, or you can pull both 3D and 2D dimensions off your object. So I like the image that I pulled there for the airplane, because that's clearly a case where you have a very complex shape, not something you're going to use a tape measure to check, and certainly something that's not going to fit in an inspection lab to use a coordinate measuring machine. Okay, so first thing when we're going to be doing this CAD part inspection is we import our scan data, which is going to be often some coordinate system depending on what scanner was used. And then we need to align that to our CAD file before we do any kind of comparison. So you can have a choice of doing like a quick fit and then a best fit to overlay your scan data, or you can do more of a datum-based alignment where you pick a plane, a line, and a point and orient your data that way. So which method to use really depends on what you're trying to accomplish. So a good rule of thumb is if you want to ship the part, use a best fit, because that's going to distribute all your errors evenly. If you want to find out what's wrong with it, then you want to use more of a datum-based alignment. So first step, after we've done our alignment, is we can do what's called a 3D comparison, and that's where we get this color map. So you set an overall global tolerance of, let's say, 5/1000ths of an inch, and then everything that falls within that tolerance will show up green. Anything that falls out on the high side will be red. Anything that falls out on the low side will go blue. This is a very good tool for a quick overall check, as well as to communicate those kind of issues to, let's say, non-technical people, your management team and that sort of thing. Because those folks won't have to flip through reams of technical reports to find out what the issues are. It's like, there's the red spot, that's where it's wrong. We put a little annotation there, it shows us how much it's wrong by, and that gives us some very quick direction regarding how to correct things. Similarly, we can do that kind of comparison in 2D by cutting a cross-section, right? And then that'll also allow us to do a whisker plot, so you can see down on the bottom of that lower image where those deviations are then magnified, especially when you're talking about small numbers, and it really helps to visualize where your issues are. And again, quickly you can communicate where the problems are, put annotations, and it makes it easy to take some corrective action. So in addition to doing those kind of more graphical analyses, you can also do 2D and 3D dimensions. So this is where you pick a feature off the CAD model, and then the system is going to interrogate the underlying scan data. So you get your nominal value off the CAD, and it pulls the related measured value right off the scan, and can do those comparisons that way. So pretty much any sort of dimension that you will see on your 2D print, you can pull off the CAD file in that way. Additionally, most inspection software today allows you to do the full suite of GD&T functions, so your concentricity, parallelism, true position, all that kind of stuff. And you don't really have to be an expert in GD&T in order to use these GD&T functions. You get a parallelism box on your drawing, you pick the parallelism button in the software to pick the appropriate features. So it's very, very easy to set those up. So again, the type of software that we use, typically in-house to do this kind of work, is Geomagic Control X. So this is the sister product to the Design X. Again, all the tools to import and align your scan data, the 3D color map, 2D cross sections, as well as all the dimensioning. And one thing I didn't previously mention is that all this stuff can be reported quickly. Again, one mouse click reporting will put all that into a nice comprehensive report for you. You can also do batch processing, where once we've selected all of our dimensions and features on the first part, we just need to import the scan data for the subsequent part, and the same report can be generated automatically. So that really helps batch process if you have several different parts to do, so several different iterations of the same part. Okay, so now we're getting into just a few different case studies of 3D scanning applications that we've done over the past few years. The first one here is Champion Motorsports. So this is a case where our customer was going to be designing add-on equipment for some Porsche race cars. So of course they didn't have the CAD files for the car from Porsche, right? So we went down there with a Creo 4 Metroscan, scanned the entire car, and we delivered both an STL file to our customer as well as a rapid surface model. So that was close enough to the original where they could use that as a starting point to design their aftermarket accessories. Another one of our customers is Arma Laser. They develop laser sights for handguns. So again, they don't have the CAD data from the original manufacturer, so they'll send us the gun, we scan it, develop the CAD file of the gun itself, and then they can use that now as the starting point to design their laser sights. So that ensures that their design is going to fit the original. Another firearm application. This is a case where we had a custom pistol grip, so they'd taken an original design and manually modified it with clay, and now they want to put that in production, so of course no CAD data for that. So we're able to scan that, clean out and smooth out those hand worked surfaces, and then generate that final CAD file. So that's another good example of what we call a hybrid model, where the exterior was surfaced, but the interior, with all the geometry, is feature-based. This is for Ocean 5 Naval Architects. They're developing, I think they're called strakes, some sort of hydrodynamic features that would go on the bottom of the hull. So they just needed from us a point cloud, and they were able to do their design work from that. So this was done using a long-range scanner, which will allow us, in multiple setups and positions around the boat, we're able to scan that entire hull. We deliver to them the point cloud, and then they can use that as a starting point for their design work. So this is a case from Stryker, which over in Lakeland is doing what's called medical reprocessing. So a lot of devices and surgical tools that they use in hospitals, historically one-time use and then they're disposed of. So Stryker is doing what's called medical reprocessing, where instead of throwing those items away, they're basically thrown into a recycling bin. They clean and sterilize all those, and they're able to repackage them and reuse them again. However, there are certain devices where there are certain components that typically will break, and as opposed to purchasing new parts from the original equipment manufacturer, there were several of these high-use items where they decided, well, let's reverse engineer these so that we can produce them ourselves and allow us to reprocess that many more devices. So this is a case where we had that small item there, we scanned it, did a parametric model, delivered that SolidWorks model to our customer, and then the last image there just shows a 3D print of the new CAD model we created, just sitting right next to that original. And finally, we have CAE Healthcare. It's over in Sarasota. This is actually quite an old project. It was about 15 years ago. So they were developing medical mannequins that doctors and nurses use to train on, as opposed to working on live patients. So they were developing a pediatric model. So we actually scanned this little boy, head to toe, and created a rapid surface model from that, and then they pulled that into their SolidWorks program to design all the components that were going to go inside. An interesting story about this, I learned when we scan people that you can't really scan hands very well, and you can't scan feet because they move too much. I didn't really learn that until after I'd gotten home and started working with all the data and realized, oh, that the hands are crap and so are the feet. So fortunately I had a kid who was about the same age as Dylan there. So we did a plaster cast of my kid's hands and feet, and then I was able to scale it appropriately and stitch it into the model of the other kid that we scanned. So it was kind of a little bit of a Frankenstein process, but it got us to the that full model that we needed. So that was an interesting project. And then here we have just a little slide showing some of the folks that we work with, here around Florida and around the country. So some names you might recognize, some maybe you know. But we've been doing this for about 18 years now, and work with a lot of companies throughout the country. Well, hey, I'd really like to thank everybody for taking time out of your afternoon to come and see my presentation. I certainly hope everybody enjoyed it. If you have any questions or anything, we will be set up. We're in booth 203 over here. If anyone would like to see any of the scanner operation or have any other further questions on any of that sort of thing. So, thank you all for coming.
Thank you.